Just to recap, if we've got a charged capacitor and it switches into a circuit with a resistor capacitor combination, you can create a voltage impulse. And that's used for testing equipment, etc. Similarly, with the current impulse generator, you're discharging a capacitor into a device under test. And you maybe are controlling the shape of that waveform with a resistor. So one of the challenges is that your components are not always rated for the voltage levels that you need. So if I refer to this table here, and let's just refer to 132 kV, your withstand voltage is 250 kV peak. So it's difficult to get components such as capacitors that are rated that high. Difficult to get a number of things that are rated that high. And it's not just on your charging circuit as well. Right, so one of the ways that they came up with was that you can combine stages of devices. So this is what's called a Marx generator. And I'm going to ask you to follow the circuit and ignore these sphere gaps or switches. So if you've got a voltage DC coming in, so look at your first stage there, it's charged up to a voltage, and it's earthed at the top in this case. Right, you can see the earth over there in the corner. So if you follow R dashed, you can see it's at the same voltage. If you follow the other side, you can see it's effectively earthed through that resistor. If again you follow R dashed, you can see that this point should be at the same voltage as this. And again, if you look at the top there, it'll also be at earth. So let's do it again. That point there will be the same as that voltage, as that voltage, as that voltage. And that point there will be the same as the earth. Right, that makes sense to everybody? Right, so the basic operation here is that we are charging in parallel. If we sketch it as a parallel circuit, you can sketch it out like you can see in number 1. And if you follow R dashed and R2 dashed, you can see where the voltage goes. But let's look at the case where these switches, they're normally little sphere gaps. Let's just close the switches, just instantaneously. Right. So suddenly, that point is connected to that point. So the voltage at this point, even though it's inverse, will suddenly be VDC plus VDC. Let's follow it again. This point here will be the sum of all these voltages. So 3V. Let's do it again. This point here will instantaneously be 4V. So we've actually increased our impulse generator from needing very big components to be a set of smaller components. Right. Right, so if we sketch it out again as a circuit, it'll look something like this. It'll look like we have capacitors in series and resistors in parallel with that. We can also add a front time resistor and our load or our measurement capacitor. So if you just look at that, doesn't that look familiar? It looks like a capacitance in parallel with the resistance. So if we go back to our single stage impulse, the capacitor in parallel with resistance, it's got a series resistance there, but when you work it out, it's a similar sort of arrangement. Right, so that's just a clever way to increase your voltage output by using lower rated components, and that allows you to have a smaller circuitry on the input, and it allows you to build it up quite nicely. Right, the second part of the lecture today, I wanted to go through the code that I've put onto Moodle. It's called impulse.m. So the first, if we just look at tutorial 3, the first couple of components there are what we did in the lecture and should be recorded in the video notes as well. And you should be able to understand and comment and present that nicely in a test. Let's look at the second component of it. Determine the parameters, what parameters are required to produce a standard lighting impulse with a voltage peak of 100 kV if C1 equals 1 microfarad and C2 equals 2 nanofarads.
Sorry, sir, can you please zoom in?
Can you download the tutorial 3, please?
Yeah, okay, I'll just download it.
Right, so what you should see on your screen is some code. I've got my basic parameters for my voltage impulse generator down here. I've got an R1 and R2 and C1, C2 and a V. That V refers to your DC voltage on the input. So the question was asking us what parameters do we need from R1 and R2 to produce a 1.2 by 50 waveform. And it gave us C1 at 1 microfarad and C2 at 2 nanofarads. You can see below what I've entered that it calculates alpha and beta. It also gives a time to peak using the equation that was derived. And it also gives the voltage at the peak. T50, you can see there, I've just defined it as 50 microseconds. And then V50, all I've done is determine the voltage at 50 microseconds. And I've also defined the efficiency. So T, I've just made an array of time. I've made it up to 50 microseconds, but let's make it 100 microseconds so that we can see a full picture of everything. I give my voltage Vt, and I use that T that I've defined above in the voltage equation. Right, and then I plot it below. So I'm just going to run that and see what we get. Right, so figure 3 in this case is the voltage. What you can see, if we just look at time to peak, TP, is our rise time is 5.8 microseconds. At our fall time, V50, we've got almost 100 kV. If we want a 1.2 by 50 microsecond waveform, this is not currently at the right sort of place. So we must recall from the notes that R1 effectively controls the front time and R2 controls the tail time. So let's change R2 first and just see what we get. So I'm just going to change it by a factor of 10, and I'm going to rerun the code. Right, again, you can see that at 50 microseconds up here, it's not close to 50% of the peak. What we can see from the code, TP is now equal to 4.4 microseconds. So we're getting a bit better. Let's now try change the front time. Let's change it down to 100 and run the code again. Our time to peak is now down to 1.7 microseconds, but our tail time is not quite there yet. So we're going to have to change that again. You can see by reducing that R2, you're constantly reducing that time, that fall time. Let's try it one last time, and then we can move on to the next example. Right, so we're still not there, but you can effectively see how we go about getting down to the right value. All right, so for next week's test, I'm going to make it a little bit longer. So I'll open it up a little bit earlier, but effectively I'm going to give you a question. It's either going to be the voltage impulse or either the current impulses. I'm going to give you some values, and then you're going to have to run the code as part of the test. And it's a simple code, so you shouldn't have any problems with it. The one thing that I'm going to show you now is something that everybody seems to forget. You should never screenshot in a submission. You should always save the file properly. Right, so it's not too hard to save a file properly. It's probably faster than screenshotting. Okay, let's move on to the second example. I'm just going to reshare my other screen. Right, so we've got a periodically damped oscillating impulse. Again, you should be able to derive that. And you should also understand that K pi over there. So we've got a capacitance of 50 microfarads, a charging voltage of 25 kV, and we need to determine R and L to produce 8 by 20 microsecond waveform and a maximum undershoot of of 20%. Right. I've also given a hint here that your inductance must be 2 microhenries. So again, I'm going back to MATLAB. Has the MATLAB screen come up yet?
No.
Okay, let me try share again. All right, there we go. So we're going to go to periodic current impulse, and we'll plug in some of the values given. So our capacitance is 50 microfarads, our inductance 2 microhenries, our voltage 25 kV, and we've gotten a periodic waveform. So we know that R must be less than the square root of 4 times L divided by C. So we're going to start with just 0.5 times the square root of 4 times L divided by C. Again, you can see all the equations are written out here. We've got our time to peak again, our current at the peak. We've got our time to the overshoot. So if you look at that equation, it's got plus 1 times pi. Right, it's got our current peak at that overshoot, and then it's given a percentage here. Again, we're going to start. We have a time array. Yeah, I'll leave it at 50 microseconds, and then we've got current based on the equation. So let's run the code and see what we get. Just going to run this for a little bit longer. So let's go through some of the values. Our time to peak is 12 microseconds. Our current at that peak is 68 kiloamps. Our time to overshoot is approximately 50 microseconds, and our peak at the overshoot is 10 kiloamps. Right, and you can see it in the plot there. There's your time at the peak. There's your peak and your time to peak. And here's your overshoot. Our overshoot as a percentage is 16%. Right, if we wanted an 8 by 20 microsecond waveform, you can see our front time isn't quite there yet. It's getting close, but it's not quite there. If we look at our tail time it's just over 20%. Sorry, 20 microseconds. It's approximately there. So what can we change to maybe increase that front time and decrease the tail time? Let's again look at our resistance and just reduce it. So reducing the resistance should make the capacitor discharge faster. Right. So what you can see here is that the peak is definitely higher. The overshoot is also higher. We haven't changed that much. Our times to peak. Yeah. Our time to peak is now 13 microseconds and our tail time is 46 microseconds. But it's definitely discharged everything a bit faster or with more energy. Right, the one other trick with your current impulse generators, remember that dIdt. So maybe let's try and reduce that dIdt a little bit by reducing the inductance. Right, so what you can see by changing the inductance is that I've got a much faster waveform. The peak occurs at 9.8 microseconds. The peak current is also much higher. It's transferring the energy from the capacitor much faster. If we look at our overshoot, it occurs much faster, 30 microseconds. The issue here might be the value of that overshoot, 55 kiloamps. If we look at our tail time, it's definitely faster. And we can probably confirm these with the values. Let's do one last iteration. We'll increase the resistance again. Right, so that's looking much better. You can see our peak is still quite high, our waveform is still quite fast, and we've greatly reduced that undershoot. Again, if I need to save this, I can just go to Save As and save it as a PNG or whatever I want to. Much easier than a screenshot. All right, so again, the test is going to include one of these impulse generators, and it will include you using the code to determine some values. And the last point is that I will open up the test a bit earlier so that you've got time to play with the code.